So, do you have any questions from the last times? Okay, so let us continue the topic we started the last time, namely, it's about performance. Let me remind that it is a theory of the action 1 over, so either 1 over 2 pi psi d bar psi plus psi bar d psi, or it's for the real fermions. And for the complex fermions, it is 1 over pi integral d to z psi star d bar psi plus psi bar star d psi bar complex. And they have the following OPs. In the real case, and by the way, I don't remember if you computed this. What do you think? What kind of OPs will they have for the complex case? So in principle, we should specify 4 such, 3 or 4 such OPs. Or maybe 3 would be enough. So so it's for the real. It's for the complex. Psi star of z, psi of w, psi of z, psi star of w, psi star of z, psi star of w. So what will we have?
When I have psi and psi star, they have to be 0.
Well, if it is at z and w, it means that they are regular. In a sense, if you multiply them at 2 neighboring points, there is no need for this function to vanish, but so it vanishes only when we send z to w. So, but apart from that, there is some Taylor series, and the first coefficient in this Taylor series is d psi times psi, which is non-zero. So and this is also regular. So zero. And this regularity is enough for commutativity or anti-commutativity of modes of this size. And for this OPs.
Get something like the real, but
why something just the same? It's the same fermionic Gaussian integral. The only difference is in the overall coefficient, but we still need to invert this operator. So it's 1 over z minus w, and this is also.
without any conjugation.
What kind of conjugation can it be? This star is the star denotes just a different field with opposite charge. So but it is holomorphic because equations of motion. So uh, so delta. Uh, uh, so equations of motion for this delta S complex. Uh, psi psi star psi bar psi bar star. Well, at the moment not equations of motion, but just variation. Uh, so it is the integral. So is it obvious? Hmm? That it is the variation of the section. And if we ask this variation to be zero, hmm, it tells that the bar of psi equals to the bar of psi equals to the bar of psi star equals to zero, and d of psi equals to d psi bar star also equals to zero. So it's first order action, and so equations of motion are also first order. So and so psi and psi star are holomorphic. Psi bar star are anti-holomorphic. Is it fine? Yeah. And so we also computed the algebra of this size, namely the anticommutator of their mode. So we have some expansion for psi, which is sum over well, um, let me right. So in principle, we can have different options. This might be z p in 1/2 plus z, which is the in case of a sphere without any defects. And this is our preferred option. Or it can be just some over integers. It is called a Ramond sector. And this expansion is psi p over z to p plus 1/2. So an anticommutator of this size was psi p was psi q equals to delta p plus q 0. So in particular, uh, if if we work in the Ramond sector, we have this anticommutator for psi 0, and it tells us that psi 0 squared equals to 2 psi 0 squared equals to 1. So psi 0 should act by 1/2 or minus 1/2. 1 over square root of 2, sorry. Hmm? Hmm? Ah, see. So it's for this one-dimensional case, but in principle we can have many such fermions. For example, this is what happens in the superstring. Uh, so another option, another situation that can appear here is the following: we have psi mu's with some index psi nu with well, so it's the same space-time index, and this anti-commutator will equal to g mu nu. So this zero modes of Raman fermions form a representation of Clifford algebra. But if it is one-dimensional case, we can just diagonalize the space here. Okay, in this case, this expansion goes as follows. So psi psi maybe let me write some generalization of this multi-component case here. So in general, so by default, this expansion for psi should go over integer or half-integer indices. And people usually choose summation over half integers. But it turns out, so for psi star it is on this one. That right as before. So the anti-commutation properties of this psi stars are the same. The anti-commutator of psi with itself is 0. Anti-commutator of psi star with itself is 0 as well. But so by default there are these expansions, but we can also perform some modification of this psi by adding here some arbitrary complex number plus sigma and here minus sigma. uh, we will see some motivation for this number, but for now it is just possible to add this because if you look at this local P of psi star of z psi of w, this shift of power of z will not change anything because if we perform some global analytic continuation around zero, they will be multiplied by opposite phases. Uh, so this local expression is still single valued, and this is the analog of this Ramon versus Navier-Schwarz for the real fermions. In that case, we can only multiply. So in this case, monodromy of psi around zero can only be 1 or minus 1 because it was the only symmetry of this action. But in this case, it can be an arbitrary phase because this action has more symmetries. Mm. Uh, well, but for Navier-Schwarz, we just don't have psi zero. This is the point. And also, I wrote it like this, and that it can be done only for I wrote that only something like this can be done. But in principle, if you have more fermions, like if you have two real fermions, we can turn them into single complex fermion. And once we work with a complex fermion, we can do, for example, size thing. Or in other words, if we have some real fermions, we can break this rule that they should be either Ramon or Navier-Schwarz. We can just add such kind of twist which will mix many of these fermions. In a sense, we can add some monodromy valued in SON. So that when we take this n fermionic fields and go around zero, they will be transformed as some vector in SON representation. So they will be multiplied by some orthogonal matrix. So we can take some twist some matrix in ON actually, and ask that psi mu of e to the 2 pi I z equals to sum over nu O nu psi nu of z. And if you want to write some explicit realization of so it is I've chosen different name for this matrix, the G mu. So if you want such kind of transformation, you can just diagonalize this orthogonal matrix, and then write such kind of expansions corresponding to different eigenvalues. So, Oh, actually, I don't know. I don't know if it has some physical interpretation. No, probably it has. Uh, it uh, it should be a so-called uh, orbifold. I think. Mm, in the sense that we have some orthogonal rotation which appears when we go around some point on the worldsheet. So, mm, so it means that there should be some uh, maybe hypersurface. Mm, yes, it should be some hypersurface in the target manifold. Uh, such that the strength that propagates in this target intersects this hypersurface by some word line, and this no, it should be something indifferent. So it's not word line; it is some point on a word sheet. Mm. Or maybe it's correct to say that it should be some codimension 2 defect. Mm, no, actually, never really thought about this in this picture. But from CFT, but zero mode in this case become a kind of non-zero modes. Because they're shifted by the eigenvalues of orthogonal matrix. Yes, but it is this Ramon alternative. But I'm saying that in principle we can insert arbitrary orthogonal rotations and ask for such transformation properties. And if it is a complex fermion, we can do the same, but with J-line matrix. Mm. And we should have and the same for upside star. Of bit maybe G minus 1 transposed. Like this, so that preserve their U1 charge and the anti-commutation properties.
G is a UN
Yes. No, not necessarily UN. It can be arbitrary JLN matrix. You see, it preserves commutation. It preserves anti-commutation properties in any case. So if you ask for some unitarity and and for kind of reality of the section, we need to make it unitary, but in general it works for arbitrary JLN matrix. Because here we don't even care about psi bars. Yeah, and if this matrix can be diagonalized, then we reduce to this previous situation. So we can choose a basis in this fermions such that the section such that it acts on each pair of psi and psi star independently in this way. So there are these twist fields, and they're useful because you see that they add some parameters to this algebra, and this can be used to construct fermionic realization of Varma modules with arbitrary dimension. Okay, so this is called twist fields. There is also another remark that actually this real and complex fermions are not so much different, namely because a pair of real fermions is a single complex fermion. So namely, let us consider the action 1 over 2 pi integral of write only the real part, psi 1 d bar psi 1 plus psi 2 d bar psi 2 d2z. So we can introduce the new fields we can introduce psi equals to psi 1 plus psi 2 plus I psi 2, and psi star equals to psi 1 minus I psi 2. And if you want to have the same anti-commutators, we should put here 1 over square root of 2. And in terms of these fields, this action becomes 1 over pi integral of d to z psi star and d bar psi. so it is like x1, x2 coordinates versus z bar. So rotation of the kind psi1, psi2 goes to maybe some orthogonal matrix times psi1, psi2. So this is equivalent to psi goes to let me think about signs. Maybe this one. Mm-hmm. So there is a morphism between U1 and SO2. This way of writing this fermions as complex fermions is just a way to write this isomorphism in some nice way. So in principle, if you have uncomplex fermions, it is the level of algebras. It is the same as to have two n real fermions, and but if you want to mention that they are complex, we preserve this additional symmetry that psi's and psi stars should transform by this inverse matrices. But actually, such a representation in terms of complex fermions is useful even for the real case, because when people study orthogonal groups in this standard Lie algebra theory. The nice basis in this algebras comes from this representation of real fermions in terms of complex ones. In a sense, we see that and that there is some manifestation of a GLN group defined on the complex fermions. But if you forget that they are complex, this the group becomes bigger, so, and it turns into SON. So this formulas realize some embedding of GLN into SO2N. So this is an embedding of GLN. So, and in particular, Cartan Chevalier basis of this so 2n comes from mostly from Cartan Chevalier basis of not actually of J1 but of SON embedded there.
Sorry. For the real case, we were able to take the matrix in ON. So we for the n equal 2 we get O2. So what about the parity?
What parity?
The parity in O2 that is not in SO2. How does it happen on the complex?
But why it's mm, okay. Let me think. Yes, it is true. Mm, yes, there is this automorphism. Because yes, it acts precisely like this. Thanks. And it will be also the case here, I think. Yeah, so any other questions?
And for the generic case, you say I take G in GLN, but then when I have just one complex fermion, I need U1, so I'm taking only phases. But in this, why can't I
No, but
arbitrary numbers?
because this alpha should not necessarily be real. So, so in principle, all this can be written for the algebras. No, better to say that it can be written for the complex groups. So we don't have any real structure here. So we can just put here gel and C, and here SO2 and C. So so this can be written like gel 1C is isomorphic to SO2C. So this, for example, this sigma here can be arbitrary complex number. It's all the same for the algebra. Yeah. So any questions about this? Okay. So let's go further. So we have this CFT, and the first question about it is about CFT is what is it energy momentum tensor? So let us start with the real fermions. Actually, it is it is easy to see that you have only one field of dimension 2, and this field is d psi times psi. with some coefficient. Actually, it should be I denote it by alpha. Mm, I denote it by alpha, but we will see later that this alpha should be equal to 1. Only to check that it is actually the energy momentum tensor. So first of all, that it has a correct OP with size. So let us compute this OP with psi of W. And since it is a free theory, we can say that this normal product is just normal ordering. So this is of Z psi of W. So first term is this. And a second term will contain a minus sign because we need to move this, we need to exchange this fermions before computing this pairing. So it will be minus alpha over 2 dz, dz of 1 over z minus w times psi of z. So maybe let me just replace this alpha by 1 because we know the answer. So what should we do with this expression to get the actual P? Mm-hmm. Yes. Yes. So this second term becomes psi of W over Z minus W squared 1/2 plus D psi of W over Z minus W plus IUR. So it is correct. So delta of psi equals to 1/2 actually. And now let us compute central charge of this theory. So we need to compute OP of the energy momentum tensor with itself. Actually, we can compute this using that technique with operator state correspondence, but I think in this case it is easier to do this using usual fermion OPs. So it is not so hard, and that technique is more applicable in some complicated cases. For example, when this basic field is not a free field. For example, for Cosmode algebra, which we will hopefully also consider today. Okay, so let us compute this OP. This is 1/4 d psi times psi, d psi of W, psi of psi of Z, psi of Z, psi of Z, d psi of W, psi of W. So there will be 4 different pairings. So no, actually more. So there will be pairing where we pair these 2 fields. It will be dw over 1 over z minus w, dz over dz of 1 over z minus w. It is this pairing. And there will be a cross term with minus sign where we compute pairing between this field and this field and this and this. So it is d dz dw 1 over z minus w times 1 over z minus w, 1/4. So there are 2 terms with 2 pairings, and then there are terms with a single pairing. There will be 4 such terms. So the first is when we pair this psi with this d psi. So it will be dw 1 over z minus w 1/4 d psi of z psi of w plus 1/4. So another term is when we pair this with this. So it will be dw 1 over z minus w psi of z d psi of w. And then 2 terms with a minus sign. First is when we pair these 2, z minus w d psi of z d psi of w minus 1/4 and 2 derivatives. Any questions?
The terms are the same.
No.
Of the second line.
Yes. Thank you. Yes. So this derivative is in z, and this is in w. Actually, I'm not quite sure that it is shorter than this computation with operator state correspondence, but no, maybe it's shorter. So is this clear, or are there some questions? Okay, so now we simply need to compute these terms. This will be 1/4 minus 1 over z minus w squared fourth. So one derivative is in z, another is in w. Mm. And here we'll have a factor of 2 because factor of -2, because when we differentiate the first time in w, we just get z minus w squared, and when we differentiate second time in z, we will have a -2 over z minus w cubed. So it will be plus 1/4 2 over z minus w the fourth. So now this one. And this one. Minus 1/4 so, and here the same. The derivative will equal to -2 over z minus w cubed. For changing the sign, it will be 2 over z minus w. Zip save w. Okay, so these two terms already give us the central charge. So it will be 1/4 over z minus w squared. So now we need to expand the. Now we need to write everything we have in that term. So it is this term, and there is this one. Right. Now this term. And uh, so what happens when we try to compute the second term in this expansion? What will it equal to? So what will be the coefficient in front of 1 over z minus w? Hmm? Uh, hmm? Hmm? No, if you expand, so we need to expand this in z around w. So what will it be? Mm-hmm. And what is this? So
It's a piece of the derivative of t combined with t squared psi psi.
Uh, no, but I actually want to say, so we can write this in principle. Mm. Now, for example, what would you say if it was psi of z, if it was normally ordered psi of w, psi of w? And I just want to say that it is zero because psi is a Grassmann field. So one explanation. Another explanation is that if we try to compute OP of anything with um, so if we try to compute some OP of psi of z with d psi of z, d psi of w, d psi of w, it will be what 1 over z minus w uh, squared d psi of w minus 1 over z minus w squared d psi of w. So in other words, we can also say that d psi of x, d psi of y equals to minus d psi of y, d psi of x. So d psi, and this is true under the normal ordering. So normally ordered d psi of z and d psi of z equals to 0. So if it was not normally ordered, then this operator just would be not defined because it would have a singularity. But if you normal order it, then it becomes just 0. Is it fine? Mm. Okay, so this one is 0. Um, so it was this.
So if I do it normal order, I will get the derivative of psi z like psi w equal to 1 over 0 stuff.
Mm.
I just take no, because it's at the same point.
Yes. So if we take self z, self w, we cannot send z to w because it will become something singular. So such field will not make sense, and the correlators uh, even in the vacuum case. But if we remove the singularity by normally ordering it, then it makes sense to send z to w and then say that it is zero. So it is a kind of quantum counterpart of a classical anti-commutativity of psi. So if it is psi in the path integral, then it is natural to expect that psi of some points squared is zero. And this is true actually up to the fact that we need to write some definition of the quantum operator psi of z squared. So this singularities coming from QFT appear even in such simple cases. So even though it is a quadratic Gaussian integral, and the operator we want to define is just psi squared, we still need to do something. Mm. Okay, so it was the second term, and now we have two more. But this one is simple. We can just put z equals to w, so other terms will be regular. So it is minus 1 over z minus w. Mm. So where is the psi of w, psi of w. Plus, so and this one is more complicated. We need to expand it around the second point. So there is this term, which is 0.
Sorry, what is the first piece?
Hmm?
Where does the first piece come from? Minus 1 over c minus
It's this term. Ah, yes, yes. Thank you. Yes, yes, and it is 0. Yes. So, and the other part is regular. So there is this term which is 0. Then there is a derivative term plus 1/2 1 over z minus w squared the psi w, psi of w, and plus the last term, which contains already in the second derivative. So it will be 1/4 d2 psi of w, 1/4 1 over z minus w d2 psi of w, psi of w. So now let us collect all these terms. So if we don't have a cubic pole, we have quadratic pole. So what do we have here? We have 1/4 psi times psi. I'm writing just psi's, meaning that they're computed at W. So there is minus 1/4 times this. And there is also this term, plus 1/2 psi times psi. Yeah, so we have this, and now what about the first order pole? This 1/4 d2 psi times psi. And there is this last term plus 1/4 d2 psi times psi. So all these terms are actually the same because this one has minus sign, but it is psi d psi. So we can reorder them. And it gives the actual OP of the energy moment tensor. This coefficient is 1/4. So what is the value of central charge here? Mm-hmm. So in principle, we can do the same for the complex fermions, but it is easier to say that complex fermions can be realized in terms of real ones. So mm, let us do this, saying that psi1 is 1 over square root of 2 psi plus psi star, and psi2 equals to 1 over I square root of 2 psi 1 minus psi minus psi star. So this energy momentum tensor maybe can I make this explicit coordinate dependence? So energy momentum tensor of the sum of two CFTs is T1 plus T2. So it is 1/2 times psi plus psi star d psi plus psi star times C plus psi star minus 1/2 everything is normally ordered. So hmm? Why? Hmm? Yes, thank you. So now let us see which terms we have here. So in principle, we could have the psi times psi, but this cancels between the two terms. And the same for psi star. So we only have cross terms. One cross term is the psi times psi star, and it appears twice. Here and there. So we will have 1/2 the psi times psi star. And we will also have a complementary term 1/2 the psi star times psi. So that's all. And, what is the central charge in this case? Mm-hmm. And so also it was better to compute this energy moment tensor in this way because in the real case we had this argument that there is just a single field of dimension 2 that equals to this the psi times psi. And here it is not so obvious, and since it is just not true that there is a single field of dimension 2. And moreover, in this case, there is a field of dimension 1. And what field is it? What do you think? Mm-hmm. Oh, I would call it psi star psi, but matter. So I want a chart of this psi star be 1. So, and if you compute mm, so, since it is a field of dimension 1, it can be identified with some one form, and this one form is a conserved current. In some sense, it can act on the space of fields. So the first question is, what is the OP with of this J of Z with psi star of Z of W? Mm-hmm. Yes, thanks. That's regular, which I will omit sometimes. And what is the OP of J of Z with itself? can write it. So what are the possible pairings? Which comes from this pairing, right? And but let us write. So in principle, we can understand from the very beginning that it is the only expression we have. But let us first write this. So this is for sure it is this pairing. But in principle, we could have this pairing, 1 over z minus w.
Yes, so that is when I put a W 0, and when I expand the regular.
So it is this plus psi star of z psi of w. When we expand around w, they become they become opposite. It can be understood from the very beginning because the field that appears at 1 over z minus w. No, maybe we can say it even simpler. So this expression is symmetric in z to w. So if you exchange z and w, it should be symmetric. So it cannot have the first order pole. It is the same as for the experimental tensor. It could not have third order pole because on the left-hand side was symmetric under this exchange of z and w. So it is 0. Do you remember something like this? Like this? And like this. Yes, precisely. This is so this J realizes this U1 symmetry. Maybe it's better to change sign of this alpha to make it consistent with everything. So Q of psi star is 1, and Q of psi is minus 1. And by the way, what were the fields that have such properties in the bosonic case? I defy. And what about such field? What was the field that had OP starting from OP that looks like 1 over z minus W, in a sense with coefficient 1 here. Maybe. Oh, what is art like this? So what was the OP of G of Z with e to the I alpha phi of W? Mm-hmm. Mm-hmm. Yes, thanks. So we can identify this psi star with, maybe it's better to say that we identify it in this way. So psi star can be identified with e to the I phi. Psi can be identified with e to minus I phi. And all this is also consistent with the fact that a dimension of this field is what? Mm-hmm. Yes. So if alpha is plus minus 1, then this dimension is 1/2. So we see that this fields have uh, the same OPs, right? Uh, and this is called of bosonization or fermionization. This transition from psi to phi. This is or boson fermion correspondence. What is important here that we have only 1/2 of this field. So it's only a homomorphic or anti-homomorphic part. In principle, we do not have such fields in the path integral. It is something a little bit artificial. But if we define them formally, then we can do such some computations, and then at the end switch to the fields which are present in the path integral. In a sense, we can always combine this. Homomorphic and the anti-homomorphic parts, and compare what we have on the fermion side and on the boson side. In a sense, For example, we'll have some fermion bilinears which will equal either to some phi squared or to exponent of phi. Thus, we can combine holomorphic and anti-holomorphic exponentials by multiplying psi star by psi bar, for example. Okay. Are there any questions about this? Uh, yeah, actually,
I have a question about before we say that we knew that in JZ, JW there was no single pole because it is symmetric.
mm-hmm.
We say also that we knew that that would be the case also for P of Z, P of W.
Yes.
But that we found we didn't find the triple pole, but we have a simple pole.
But this simple pole comes, so where can maybe I can erase, I can write it here. So we have this we have this first order pole, but this expression written here is not symmetric, and exchange z with w. And if you write it in the symmetric form, it looks like this. One option is to write it as a t of z plus t of w over z minus w squared. So is it clear that if you expand it at w, you will get this expression? Another option is to expand it around the intermediate point. Pythagoras. So from some algebraic computation point of view, this should be a better representation because we always expand around the second point, and it corresponds to some action on the a space of fields of a space of states. But if you want to write some algebra in condensed form, and write some OP of field with itself, it is better to expand around the intermediate point. One option. Another option is to symmetrize it this way. So it becomes especially obvious that it is a better representation if you try to write some OP for the W algebra, which contains a generator of order 3 in the simplest case. So it has a 6th order pole, and in principle, if you write it in non-symmetric form, we will have fourth order poles, third order poles, second order, first order. But if you write it in such symmetric form, it will be 6 with some numeric coefficient, and then fourth order and second order poles. So it's some life hack how to write the relations in some vertex operator algebras. if you want to write them explicitly. So is it fine? Hmm? Yes. So phi of z. So dimension of this. So if you write here homomorphic and anti-homomorphic dimensions of this pair, then it will be alpha squared over 2 0. And by the way, so far we only know that they are proportional up to some coefficient, because we have computed the OP of J with psi, but we have not computed the OP of psi with itself and with psi star. So in principle, they can contain some trivial coefficients. But we'll do it now and see that the correspondence is actually with coefficients 1. So this corresponds to computation of this OP. I phi of z e to minus I phi of w. And let us remember what happens when we compute some correlators of such exponential fields. So correlator of e to I alpha I phi of the I, maybe, well, e phi of the k is equal to product over k less than m. So and they are normally ordered exponentials. For k less than m is in k minus m to alpha k alpha m, right? So it suggests that OP of e to I alpha k phi of zk e to I alpha m phi of zm is what? It is z k minus zm to alpha k alpha m e to the I alpha k phi of the k plus alpha m phi of the m. It can also be understood in some other way, in the sense that if you write something of this kind, that a normal order of the field that contains a plus and minus part plus a minus. So there is some a little bit tricky part related to this infrared and ultraviolet regularization, because this no, this regularization that we defined for phi contained only ultraviolet divergence, and if use this usual QFT reorder, they will contain infrared divergence, but usually it can be neglected. We can just say that infrared divergence is infrared regulator is formally put to 1, and we just remember about all these U1 conservations. So we can simply say that normal ordering works as for polynomial fields, in the sense positive modes should be moved to the right, negative modes should be moved to the left. So this normally ordered exponential will equal to e to the a plus, e to the a minus, e to the a plus. And if we now multiply two normally ordered exponentials, e to a times normally ordered e to b, it will equal to e to a minus, e to a plus, e to b minus, e to b plus. So it is something that is not normally ordered, but it can be ordered. In our case, a plus, commutator of a plus with b minus is just some number, because these operators have commutation relations like j, k, j, m equals to k delta a plus m 0. So they commute by some number. So commutator of a plus with b minus some complex number. So if it is true, then how can we rearrange these two exponentials? What will be the answer for what will be the answer in the normally ordered form? Hmm? Hmm? Uh, 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 no, so what else? No, so there is this term. Uh, what else? Mm-hmm. like derivative on what? Oh, that's cool. Hmm? Hmm? So what else? Hmm. Yes. So it's a kind of Campbell-Hausdorff formula, or maybe yeah. So it's even simpler because this commutator has just some number. This is so since positive modes commute with positive modes, negative modes commute with negative modes. This can be identified with normal product with normally ordered exponential of a plus b. So it is exponential of the commutator a plus b minus times normally ordered exponential of a plus b. This commutator, as we know, equals to the vacuum correlator of this fields A and B. So it is e to AB, e to the A plus B. So it reproduces this formula which was just guessed based on the form of this correlator. Right. Yes. So and now what we have here? We have 1 over z minus w, and here we have e to 5z minus 5w. So so the leading term is actually 1 over z minus w, and which is in principle enough to find the algebra. But let us also look at the subleading terms. So we have here uh, exponential of I z minus w d5 of w plus I over 2 z minus w squared d2 phi of w plus everything normally on plus I over 6 z minus w cubed d3 phi of w plus and so on. So if you now expand this, we see that it is 1 over z minus w plus I d5 of w plus, let us write the next term of this expansion. So it will contain square of this plus this term. Without square because we divide by z minus w. So, and I will not write the next terms. Only read this expansion, but on the other hand, this expansion can be identified. So we already checked that this fields should be identified with the free fermions. So what we are computing here is the OP of two free fermions, psi star and psi. So let us write this, and let us try to compute the OP of these free fermions as, as some expression in the free fermion algebra. So what is 1 over z minus w plus well, I forgot to say, to write that it is psi star of z, psi of w. So the first term is 1 over z minus w, and then we write a normally ordered product. So if you look at this formula, maybe it's better to write this relation before computing this actual expansion. So if you look at this formula and at this formula, we see the following relation, that a normal ordering of psi star of z psi of w equals to e to the I phi of z minus phi of w minus 1 over z minus w. And in this formula, these normal orderings are different. This normal ordering is for fermions, this normal ordering is for bosons. Actually, if people can use different notation for this normal orderings. One normal order moves the bosonic positive modes to the right, another normal order, and this was fermionic fermionic modes. Yeah, and are there any questions about this? Yes, so now let us finally compute this OP on a bosonic side and find some relation between bosonic and fermionic operators. So again, this expansion of normally ordered exponential between this. Well, this equals to psi star of z psi of w. Let me write 1 over z minus w plus psi star of z psi of w, normally ordered. So if we expand this, in the first term will be psi star of w psi of w. And the next term will be z minus w d psi star of w psi of w plus maybe no, let me maybe write one of the first terms in this expansion. So there will be mm, minus I over 24 d phi mm, I over 24 z minus w squared d phi cubed plus something plus higher terms. And here it will correspond to 1/2 z minus w squared d2 psi of w psi of w plus other terms. So if we now compare this two expansions side by side, we see that psi star of w psi of w is equal to I d phi, which is actually not very surprising. because it is precisely the formula for ion current. And the next term also is not very surprising because, well, actually, maybe it is, no, let us just write that term. So this term is d psi star of w, psi of w is minus 1/2 d phi squared plus I over 2 d2 phi. And it can be rewritten. In a sense, we can construct the term which equals to this energy momentum tensor. Namely, we can subtract 1/2 of a derivative of this term. So it can be written as d psi star psi minus 1/2 d of psi star psi. So this is 1/2 d psi star psi plus 1/2 psi d psi star. And on bosonic side, this subtraction just removes the second term. So it equals to minus 1/2 d phi squared. So this expression is bosonic energy momentum tensor, fermionic energy momentum tensor, and this expression is a bosonic energy momentum tensor. So it's not very surprising that they equal. But more interesting relation is here. So, namely, if you compute this counterpart for a second derivative of psi times psi, it will start from minus 1 over minus I over 12 d phi cubed plus some other fields of dimension 3. So it can be d phi, it can be d2 phi times d phi, maybe, and d3 phi. I don't want to compute them, and I don't know precise coefficients, but it is some operator which is nonlinear in phi. So, and we see that something that is quadratic in terms of fermions equals to some non-trivial operator in terms of bosons. And this is called, maybe I'm not sure that it is precisely about this operator. Maybe it should be corrected by some derivatives of other operators, but something very similar is called the cut and join operator. So maybe let me write cut and join type operator. So it is some operator that acts in some linear way in terms of bosons, but it's just quadratic in terms of fermions, and so it acts nicely on the fermionic Hilbert space. But for some field, so and it can be useful in some numerative problems, but for CFT applications and for filter applications in general, more useful relation is this one, the relation between fermions and exponentials without this series expansion. Then this relation will allow us, for example, to write Sun-Gordon model in terms of fermions. Not necessarily free fermions, in terms of some fermions, and for some value of parameter, they will become free. So, and I will tell this next time. So, are there any questions about this? Uh, uh, I don't remember precisely. Mm, maybe it's because it's action uh, on and to remember precise objects where it acts. So if I remember correctly, it can act on characters of symmetric group and or on or maybe better to say on the in the dual picture on conjugacy classes in a symmetric group, and it can do two things: either to glue two cycles to one bigger cycle, or to split a big cycle into a pair of two smaller cycles. Because if we write it as bosonic, it will be approximate, but if we write it in terms of JKs and operators acting on JKs, maybe let us make some identification that J minus K is identified with pk. Jk is identified with k d in d p k, so that they commute in a way we want. Then on this this operator, maybe better to say a zero mode of it. Maybe so zero mode of this thing should be called cut and join operator. So the zero modes act something like this: k m p k plus m d2 and d p k d p m plus K P plus K plus M P K PM D2 and D P K plus M. Something of this kind. Yes, because it is d phi cubed in principle plus some other terms of smaller degrees, I think, or maybe without them. I don't remember precisely. So you see, this operator. So if this operator acts on polynomials of pk's, it can find pk and pm. Destroy them and add pk plus m. So if pk and pm are identified with cycles of length k and m, then it produces a cycle of length k plus m. And it can do so. And this factor km corresponds to the fact that it can cut the cycles at an arbitrary point. There are km's to cut one cycle and m ways to cut another cycle. So it kills on these two cycles and produces cycle of length k plus m. And this is a join part. And this cut part can and this cut part finds some cycle of length k plus m, and it cuts it in 2 points. So one point is fixed, and another point can be chosen in k plus m different ways. So it cuts it and produces 2 cycles of length k and m. So it is something that acts in this non-trivial combinatorial way on this polynomials of pk's and pm's, which are identified with symmetric polynomials. And if we write it in terms of fermions, it is something simple. Mm-hmm. Yes. Hmm? Uh, yes, yes, but with some additional details, because here, so when we work with fermions, so the first question is what theories, because what theories, because here we don't have mm, anti-homomorphic counterpart, so it should be added. And the second remark is that we don't have, so in the fermion theory we have only mutually local fields, and in this boson theory, without anti-homomorphic part, we have arbitrary exponentials. So these arbitrary exponentials do not have counterparts in terms of fermions. There are some non-local fields, and they should be added manually. And also, if you try to construct the corresponding representations for the fermions, we will need to use these twisted representations. So this dual field is not some combination of fermions. It is some extra field that should be added to this theory of fermions. It is some defect field, and it corresponds to twisted representation of fermions. So from the point of view of the path integral, it means that we can insert some U1 connection with singularity at some point. But we will discuss this later. So, do you have any other questions? Okay, thanks for your attention.